So we are now going to begin recording the sessions. Again, so that'll be available for anyone that would like to review that. And I believe we are at the point right now where we're going to get going. Presentation. Team, are you ready to present?
Yep. Yes, sir.
Okay, go ahead.
All right. Good morning, everybody. This is Team Spinning Solutions. My name is Matt. We also have Emilio, Daniel, Connor, and Sarah. And we made a rotary hammer test bench this semester for Milwaukee Tool. So why did we make a rotary hammer test bench for them? So we have this rotary hammer tool, which is used a lot in industry for removing concrete and stuff like that. So there's a couple different options of the tool. There's the STS Plus and the STS Max, which you can see in this table below here. And then you can kind of see the diagram of how the general tool works. There's a pressure column that's created that accelerates the striker into the anvil, which pushes the accessory to eventually puncture the concrete and create that hammer motion. Through all of this information that we got from Milwaukee Tool, we created goals, and those goals will help us shape what we need to research, our specifications, and everything down the line.
For our background research, we looked into multiple ideas that we thought would aid in our design process. The first one we looked at was obviously the tool itself that Milwaukee Tool planned to design a coefficient of restitution test bench for. We also looked into various pneumatic systems that we thought would be relevant, since Milwaukee Tool mentioned that as a possible avenue we could pursue in terms of the design. And finally, we looked at flywheel systems that are relevant. And as you can see here in some of these images, we have pictures of various pneumatic internals and also the various types of flywheel systems you looked at, such as a football thrower.
So for the project, we need to look at both areas of the drill. Also, not only the actuation, which is how we accelerate the mass, but also how we measure the coefficient of restitution. For that, we look to two different control systems. First, an Arduino to control the actuation, and also data acquisition unit to control and get data from the sensors. We research a wide variety of sensors to be able to find the best one that accommodates to our project. And here you can see, for example, the diagram from LVDT, a laser sensor and its workings, this a capacitive sensor, and how Hall effect sensor work. For design specifications, after we came up with enough background to know what we have to do, then we came with specifications to know what we want to achieve for the project in some specific areas like performance, service life and maintenance, appearance and finish of the product, quality and testing, and the safety of the test bench. For performance specifications, we had to go according to Milwaukee Tool given performance specifications, and that's something like the diameter of the spindle, the mass of the striker that's going to be accelerated, the striker impact velocity to be able to measure the coefficient of restitution, the velocity that it needs to achieve, as of the accessory length, which is the distance that we have to be able to accelerate this mass.
In terms of the service life and maintenance, obviously we wanted to create a tool that would last multiple years with very minimal maintenance, since this is something that we're providing to Milwaukee Tool, and they would be responsible for a lot of the maintenance and upkeep of this. I didn't want to create a device that constantly has parts that need to be exchanged or sensors that need to be replaced.
For appearance and finish specifications, even though it's not the most important part of the project, we also want to be able to provide something to the customer that is good looking, that is well organized, and it's simple and easy to understand.
In terms of quality and testing, first of all, we wanted to make a device that allows us to give a pressure input and give out a velocity output. We also wanted to have that velocity output be fairly accurate within 5 significant digits. That's just something we decided upon. Furthermore, we wanted to be able to test this device and dial it into our specifications via various tests and performance tests that we can do at MSOE, LM sites, as well as once we give the tool to Milwaukee Tool, we plan on running these tests an additional time to make sure that the device is dialed in at their facility as well.
For safety specifications, safety is the most important part of the project. Not only safety when we're building it, but safety when we're designing it to be able to deliver a safe product to the client. Some of the safety specifications and stuff we are adding is like a polycarbonate shield to be able to protect whoever's doing the testing. Also a kill switch, and we're going to conduct a thorough safety inspection before delivering the final product to the client.
So now with the specifications specified, we can go into a little bit more of the actual design process we followed. So for this, we used the fire process just because our advisor had mentioned that he had done this process through with multiple teams and had the most resources for it. So the fire process consists of functional analysis, which is essentially done via a fast diagram, ideation, which is simple idea generation, recombination, which is combining all those ideas we generated into a full design, and then evaluation, where it's taking the designs we made and putting them into a decision matrix and deciding which one is the best for our solution. So here we can see our fast diagram for functional analysis. How it works is each one of these blocks is what we call a function. It consists of one noun and one verb. That's simply an action that the system needs to do before it's able to complete its desired task. So you can see on the left, we start with initializing our system. And on the right, we display our coefficient of restitution. So if we follow the diagram right to left, we can see how each of these functions work. And from left to right, we can see why each one of these functions exist. You can also see a bunch of verticality with this diagram. Simply, there's things that have to happen at the same time. So for example, our concrete impact, we need to be able to both hold the concrete and then measure the velocity of the striker before and after the impact happens.
So to start some of our idea generation for our control system, we need to kind of figure out where we wanted to go for our spindle actuation. But a lot of the different ways that we were thinking about doing our spindle actuation be controlled through a variety of different ways of microcontrollers, whether that's an Arduino, a Raspberry Pi, or an ESP32. A lot of those different options can kind of be mixed and matched with different spindle actuation, so we can do it on that side. To separate it, we wanted to do our sensor and data acquisition separately in case we had to at any time edit our spindle actuation part. So we were planning on looking at using a data acquisition unit instead, so that we can just collect all the data from there and it could be completely separate from our spindle actuation portion. The next part that we did a lot of idea generation on was velocity measurement. So we needed to kind of define how we were going to measure velocity. And we kind of defined it as just a change in distance over a change in time. So the best way to measure is to set one of those two variables. Our first design kind of sets the distance between. So this would use proximity sensors that could see through the spindle material to see the velocity of the striker. We can correlate those positions of those sensors back through the data acquisition unit and relating that to the time that's collected over the entire sample that we want, and calculate the velocities from there. The other way that we thought about doing this as well was using a laser velocity sensor. This would set our time and allow us to measure the entire displacement of the tool or of the striker to see what their overall thing is, and then get the velocities from the overall distribution there.
So now we go into some of our mechanical designs that we came up with. So this one on the left is the pneumatic plunger design, which is taking a pneumatic cylinder that has a mass attached to it at the end, putting that mass inside of the spindle. That mass, when the cylinder is actuated, will then be actuated forward to hit the striker and cause the impact interaction we're looking for. On the right, we can see the pressure vessel idea, which essentially is taking our spindle and sealing it with a gasket-like material. Also having a clamping force on the spindle as well to make sure that seal is nice and tight. And then that'll just be acting the spindle as a air chamber. Another similar idea to the pressure vessel is the air cannon idea, which has the same exact concept, but has an off-board air chamber instead of using the spindle for an air chamber. Finally, we have our flywheel idea, which is going to be taking a slug-like object and pushing it or accelerating it with the flywheels that will be spinning. And that slug will be used to hit the striker and cause the impact that we need.
All right, so now that we've gone over the ideas that we came up with, we did have to do some calculations in order to properly evaluate them in a decision matrix. So for the pressure vessel idea, we did calculations to determine the amount of pressure we would need to launch the maximum spindle weight of 0.5 kilograms at the maximum velocity of 15 meters a second. And basically our calculations showed that we'd need a little bit over 500 PSI. The problem with that is that the only compressors we found really capable of outputting that are ones commonly used for scuba tanks or paintball guns. The other issue with these kind of compressors is that they have very high maximum operating pressures, typically in the range of like 45,000 or 4,500 PSI. My apologies. Due to that being such a large number, we decided to do burst pressure calculations on the spindle itself, and basically found that it would burst at an internal pressure of about 48,000 psi, meaning that if there was a situation where an operator accidentally cranked up the pressure on one of these too high, there is a decent chance that the spindle could critically fail and would result in some serious safety issues, which will be reflected in our decision matrix. In addition, these launch pressure calculations also do apply for our air cannon idea. However, we basically just increase this X value, which is the distance the striker is traveling, which greatly reduces our pressure, our required launch pressure. I think we were finding somewhere in the range of like 100 to 200 psi, which is much safer and much more commercially available.
In terms of this decision matrix, you may have noticed that a pneumatic plunger idea didn't make it onto this decision matrix. The reason that is we determined through calculations it wasn't physically viable with the parts available on McMaster-Carr. We developed a script that used isentropic expansion, or assumed the gas to expand isentropically throughout the spindle, and it calculated the pressure required for every single McMaster-Carr pressure vessel or pneumatic plunger, and output the pressure that would be required, and it was higher than maximum allowable pressure for each of the McMaster-Carr vessels. In fact, their maximums for their pneumatic pistons was about 200 psi, and we are getting about double that for these calculations. Due to this, we determined that it wasn't viable to do the pneumatic plunger and not even worth evaluating on the decision matrix.
Yeah, so we can go a little bit more into the evaluation of the decision matrix. So below is our criteria, that being mostly 5 categories that we came up with: safety, simplicity on the mechanical side of things, controllability, familiarity, as well as size. We were able to rate both our pneumatic vessel, air cannon, and flywheel ideas. Out of this decision matrix, we were able to see that the flywheel was our best idea due to having a high score in both controllability and familiarity with the idea of the team. So with that flywheel being selected, we can go into more of an in-depth process of determining what type of flywheel system we were planning on using. So as you can see in the top left, there's a few of our ideas that we came up with, but it has a bunch of different configurations with rollers, wheels, belts, and motors, and momentum wheels as well. This is also, as we can see, the criteria here that we use for our decision matrix, being simplicity on the mechanical side, controllability, spin-up time, as well as size. So spin-up time, we were able to do some calculations with a system that we kind of spec'd out a little bit. We want to ensure that, first of all, the system was able to hit our 15 meters per second needed velocity, as well as our necessary spin-up time within a reasonable number. We can see those results of these calculations here, showing that both the single wheel with rollers and the double wheel with double motor were not able to hit the 15 meters per second we needed. So that reflects here on our decision matrix, but the other ones were able to do so. So with this decision matrix filled out, we were able to determine that the momentum wheel with a single wheel with rollers was our best idea. So with that, we can see a better picture of that idea marked out here, as well as we can combine this idea with the other controls and that part of the project done. So you're good. The controls are going to be the same as mentioned before. However, we're going to need to add a motor shield due to the motor having to run at a higher voltage. So we want to make sure we don't fry any Arduinos in the process. We also still want universal mounting with the system, as we're able to want to put eventually multiple spindles inside this configuration. Then a movable concrete block in the system, so we can ensure we're running enough tests with one concrete block, as well as prioritizing safety when it comes to our design.
All right, so now that we've defined the system that we're going to be running with, we're going to walk you through some of the CAD modeling that we did. So here you can see our spindle actuation system, where we have our motor-driven momentum wheel, which is then connected to this black flywheel via these pulleys that can be seen down here, and a belt that wasn't modeled for the sake of simplicity. You also have these 2 free spinning compliant wheels, which basically work to keep our slug in alignment as it's being moved back and forth. For actually positioning the slug, what we have here is a servo-driven swinging arm. Basically, this will push the slug until this front face of it makes contact with the back of the striker. That way we don't have any kind of secondary impact interactions that could potentially complicate the usage of the tool. Once that contact has been established, the swing arm will continue pushing the slug until it makes contact with the flywheel, which will then accelerate it. In terms of versatility, the system that we came up with basically involves these 2 yellow support blocks. These are essentially machine blocks that are going to be unique to each of the spindle geometries, but just simply bolt into the fixture to allow for quick and easy changeout times. The next system we did was our concrete holder system. So to ensure that we had as much back and forth and side to side adjustability as possible, we mimicked systems commonly seen on CNC machines. We're basically doing this by having threaded lead screws that are driven via these hand cranks so that an operator can very simply just position them however much they wish. These are being constrained by these 3D printed linear slides that will slot into these aluminum T-rails, basically. Then for our vertical adjustment, we have 4 linear slides mounted on the corners of each of the plates that are holding the concrete block itself. And then the actual motion is being controlled via a car jack, with the idea being that operator can just take a impact or a regular drill with some kind of standard socket and just move it up and down however much they wish.
So the next part of our design part is our controls design. So there's 2 parts to our controls design. Like we said earlier, there's our spindle actuation controller, which is done through an Arduino with a motor shield on top of it. We have our motor plugged into it, as well as an AC to DC converter, so that we can get from just a wall outlet to 24 volts. We also have our servo and our rotary encoder plugged in there as well, so we can do feedback control with the motor to set our speeds correctly. Separately, for our data acquisition unit, a lot of the sensors that we were seeing, they all had a very similar wiring type, whether that was PNP or NPN. Basically, it stands for positive, negative, positive, or negative, positive, negative. So basically, what we have to do for this, a lot of the sensors that we were planning on using have a higher voltage limit than what we can actually complete with the DAC. So what we have to do is inside of here, you can see these 2 diodes. You have to pull those resistors down to be able to, so we can independently power the sensors and give them our own power, and then still collect the data through the data acquisition unit to give to our computer, to give to our control system. The next part of it was our velocity design system. So here we have a test stand that we were making up for our prox sensor gating system. We're still deciding options on the specific sensors to use. We were running into a lot of software troubles for testing specifically. So we want to be a lot more confident in the idea that we're picking first before we purchase any sensors for them.
So now that we've kind of defined all of the subsystems, this is just a model we made that basically combines everything together. So here you can see our concrete system and our spindle system basically mounted together via these aluminum T-rails, basically just to make sure everything stays level with itself. You can also see here our controls board mounted on the back with these 2 holes, basically just allowing us to have really good cable management to ensure that our final product is as neat as can be.
In timeline,
So to go over the timeline, we did a Gantt chart to make sure that we stayed on schedule for our project. This goes over every single process we have to do for the project and when we have to do it for the entire academic calendar. As you notice, it labels who is supposed to be on what project, as well as the fact that there's a small gap here that you might have noticed, and that's due to the winter break that we're going to have. We may decide to fill that gap with some items to aid in our design process, but that is yet to be decided as of this point.
finally, in terms of the economics of the project, we went through a very detailed budget. It's divided into 2 sides. Firstly, there's the materials cost of the project, and also for the sake of understanding more of the economics part, we did a budget for labor. We're not going to be charging a multi-tool, so you don't have to worry about that last thing. But just for the sake of understanding, and we came within $2,000, which is well within our budget of $5,000 for the project.
So our plans for next term really are to kind of finish up our design review with Milwaukee Tool Engineers. We had our first design review on Tuesday, and we got a lot of great feedback from it, including how we can limit the scope of the project a lot. We kind of were at a misunderstanding, and maybe we made an incorrect assumption at the start, where we thought we needed to basically fit every single striker mass size into every single spindle size, which is totally not the case. And so what we have to be concerned about now is making a simpler system for the one that we currently have, and then being able to scale it properly with that. After that is completed and we officially select our design, we're going to be doing experimentation and testing your components, finally building the entire mounting and control structure, and then starting our testing with our first striker and first spindle, and then going and debugging and doing more strikers and spindles as we can do for this this upcoming term. And then we just have some references here and some questions.
Okay, so at this time, we're going to first take questions from the panels. And I think I'm going to start online with Dr. Armstrong and let him voice any questions that he's got. And go ahead and open your mic if you would.
Okay, thank you, Dr. Farrow. Can you hear me all right?
I can. Let me
It's a little bit quiet.
yeah, of course it's quiet. Let me see if I can bring this up just a little bit more. Okay,
All
go
right,
ahead.
how about now?
Perfect.
All right, great presentation. It looks like a really interesting project. Couple questions. What will be the duty load on this testing equipment? I looked through the report, but I didn't see that. How often will it be used? What's the life expectancy? What are you designing for here?
So basically, really the service life of this is kind of up to how much Milwaukee Tool wants to actually use the tester. So we're trying to make it so that they can use the tester as long as we can make it last. But it's really due to the Milwaukee Tool engineer's discretion on how long that they use the tool and how often that they use the tool.
Well, oh, go on.
Yeah, we haven't been given a specific load, you know, like a daily load or a weekly load. So we don't really know like how much is going to be used. But probably for the next semester, we're going to be actually building it, and you know, that specification is going to be needed. So thank you.
Yeah, I would certainly ask them that or get an idea of it, because that'll affect some of the decisions you make in terms of your components and the way it might be laid out. Another practical consideration, this is going to be tested on concrete. Is that correct?
Yep.
So have any of you actually used a hammer drill like this before? You have. Okay. How would you describe the process once you used it?
For using it, I mean,
Yeah.
you have to know where you're going to use it, choose your bit.
Yep.
And then you know if you're going to be drilling or you're going to be trying to break the concrete, and then you choose your function, and from there you just like go at it.
Yeah, it was pretty dirty though, wasn't it? Every
Yes.
time I've done it, I've ended up spitting out, sand and concrete from my, I don't know
Yes.
how it got into my mouth. Have you, in your design, have you thought about how you're going to handle the debris? How are you going to keep the instrumentation as clean as possible? And then there'll always be some getting in. How are you going to clean it out afterward? Is that a factor in the design?
So the first time we talked to Milwaukee Tool about this, we actually, for measuring the coefficient of restitution, we usually need to go through one cycle, which hopefully won't make too much debris. You know, as you know, like when you're using it, you go through probably like, you know, a lot of cycles per minute or per second. And here just gonna be really one cycle, hit the concrete. It may do some dust, but it's not something we're really worried about now, because it's not gonna be used constantly. Like you're not gonna try to break the piece. It's just gonna like go once and try to measure how stuff happens on the inside. So like one concrete block, it should last quite a bit, and the dust, I don't think it should be a factor. We could consider also something for design, but we're not very worried about it now just because we have to go only through one cycle.
When the tester is in use, it's not like you're actually using the tool against a wall where it's constantly actuating back and forth constantly. It just fires once, calculates the coefficient of restitution off the bounce, and then it's done. So it's not going to create nearly as much debris as it is when it's in constant use against, say, a concrete block or a wall.
Do you plan on encasing your instrumentation in some type of polycarbonate or something? Or, so for instance, if the workers there, the technicians at Milwaukee Tool, in between usage or whenever it got dusty, just sprayed it off with high pressure air or something, is that going to cause any issues in what you're designing?
So I don't believe it should. The proximity sensors, a lot of them that we've looked at, they are good for like a lot of different uses in industrial use. So they have in every single piece I've researched, they said that they can be scrubbed in dirt and then immediately plugged in and used basically. So it's just not at least for the sensors that we had initially been planning on using. But when we go back and look at it, we're gonna look more into that part as well.
Yeah,
Okay.
I'll speak up to that. So this is not gonna be used for like a technician work. It is more for like our engineers to help us with our early development in the early stages of like prototyping. So it will be like a single impact, like the team said, and there will not be like much dust generated. If we do have like in the lab, we have multiple dust extractors there that we can use.
Okay. All right. And then last question, there will be people using this though. And you mentioned that when you wanted to try a different combination, they could unbolt and bolt in. Is there anything else you can do as engineers right now designing this to make it so that the people using it will be able to test, have a higher cycle time, how many tests they can set up and do, and also anything you can do to reduce that setup time, that changeover time when they want to do something else other than simply bolting in?
I think that comes down to the overall function of kind of how we initialize our system, right? So that takes into having to do our data inputs and everything like that. So we are one of our stretch goals that was highlighted inside of here, and I believe also inside of our report, is that potentially out in the future we want to make something that could be potentially automatically reset, so that the team can just go and fire, and then if they need to go change out the striker, they can just change that single piece out instead of having to reset the rest of the system. But again, like I said, that is a stretch goal because it's not something that Milwaukee Tool necessarily needs, but it's just something that would be a lot better for the overall system use.
We also determined that there would be some challenges that would need to be addressed to do a system like that with what our current plan is.
Yep.
Okay, we've got a little bit of time left. I'm gonna see Dr. Mahinfla, do you have any quick comments, question?
I just want to know how would you measure the forces in your system, basically, you know, when you're impacting something, that force generated at that point can be a peak load. How do you figure those out? Did you ever think about that? And also, how do you look at the system that you send in impacted? How does it go back with the flywheel system that we have? Those are the questions we answered, I think.
Yeah.
So in terms of the force is like of impact is not of a lot of relevance here, because what we're really caring about with this system is testing the coefficient of restitution, which relies almost entirely on velocity, right? You measure the velocity of it right before impact, and you measure the velocity of the striker right after impact. And that will maintain the, and that will give us the data we want. In terms of the forces themselves, obviously, since we're using the same systems and strikers and spindles that Milwaukee Tool is using in their tools, there shouldn't be significant forces that should cause any sort of stress or damage to the system inside the spindle from our understanding.
In terms of our reset system for the actual slug, we haven't fully decided yet. The braking system we're currently looking at basically involves using like some sort of cable that goes taut before, obviously before the slug would travel too deep into the spindle, which could potentially interfere with the rebound interaction. So current idea was using that and maybe having it manually reset, but we haven't fully decided on that one. That's something we're going to be working on a lot over break and at the start of next term.
Some other additional ideas too were like cable retractors, like that you use for like your sign and badge as well. So that could just do that automatic motion instead of just having the cable taut.
Okay, we've got one last question coming from Austin Quer. He's the sponsor for the project at Milwaukee Tool. So Austin?
Yeah, so for your burst pressure calculations, when you're saying that pressure is gonna cause the whole spindle to blow up, did you account for all the exhaust holes that you have in that system? Or was it just you looked at the ID/OD?
For that one, we were just looking at the ID/OD due to us having like a little bit of like our understanding of how the vent holes interact with the entire thing being a little less solid, and because the whole pressure vessel like idea requires us to have that being completely sealed. So that's how we kind of modeled it for the purposes of those calculations.
Completely sealed before events, you mean?
Yes, yes.
Okay, thank you, team. Thank you. So at this point, we're going to switch over. So we'll have the Dream Bikes team stepping up. So we talking a lot about something. The direction that you make sure we're on.
I'm gonna stand on this side today. I'll be right back.
You gonna sit as a panel member? Or? Yeah. That's easy enough. Starts.
You're gonna get
All right.
good.
So take a moment and get yourselves ready. And we'll get going in just a moment. Let's room settle.
Dr. Farrell, you see me in the screen?
Let's see. Yeah, right now we can.
Excellent.
So the only person we can't see is the one at the computer.
Oh, she'll be there. Right? We have a clicker. She'll be there.
Okay.
Yeah, it works. Perfect.
You have to be careful because when you slide that way just a little bit, you're out of camera. So be careful.
Yeah, that's where I was saying.
And the easiest thing to do is since we're recording is to rotate to that middle slot before you start speaking as your partner. Okay. So audience, please respect the presenters. So side chatter, keep that to a minimum. Everyone that's viewing online, if you'll keep your microphones muted until our questions and answers period, that would be wonderful. So as mentioned before, the team will have approximately 20 minutes to deliver their presentation, and then following that time, there will be time for questions and answers. So I'm Dr. Farrow, and again, I'm acting as the chair for the session to keep things moving along. So we've got Dr. Armstrong's design team that's been working a problem. And team, are you ready to go?
Yes, yes, sir.
Yes.
Take it away.
Hello, everybody, in person and online. We are Dream Bikes. We are the senior design team that is partnered with Dream Bikes Milwaukee. I'm Michael Christie. I'm Joe Belland.
I'm Callie Resch. I'm Latian Ying.
And I'm Brenda Donovan.
And like I said before, our advisor is Dr. Armstrong. So for today's agenda, we're going to be starting with a little bit of background on the project with these first two bullets. Then we're going to shift into our design steps with the next two, and then we're going to wrap it up with the last two, talking about what we're going to be doing further and what we've concluded from the project. So our general project statement was Dream Bikes came to us and asked us to improve their showroom by adding a bike showcase system, and they wanted us to primarily use refurbished bike parts that they will be providing to us. And as a secondary objective, if time permitted, they have their basement is full of bikes. They have the largest bike supply currently, but it's a little bit messy. So if we had extra time, as an extra objective is to propose solutions for that basement storage, predominantly their wheel and spoke storage.
Ritz, thank you. So during our scope phase, we've determined some of the deliverable items for this project. We've broken them down into 4 main categories. This is the research, design, prototype development, design and documentation, project management. Notice that design is happening twice here, but that's not a mistake, because in the early on stage, we want to make sure what our requirements is aligned with our client. So we did a little bit of solution concept, analysis report, specification stuff, just to make sure it's feasible. Some of them were eliminated in a very early stage. And for prototype development is planning how do we construct our solution, as well as a secondary task, which was assigned by Dream Bike, is if time permits, we're also going to build a storage solution for the basement for the wheels and spokes. So that is if we finish our delivery by April 1st. Documentation and design is kind of going on simultaneously with just our research and design process and analysis process. So we want to make sure we get a maintenance manual by the end of this project so that our client is happy with training their future employees and maintaining our solution so that we will never have to go back and fix something for them. Project management, that's something we do to work with our advisor. We provide weekly reports for our advisor and we ask questions for guidance, as well as that final project report we just submitted this past Monday. Here are some of the acceptance criteria we've identified in the early scope stage. We determined that safety is very important. Functionality mostly deals with kind of our capacity of the storage. Aesthetics, which is one of our clients' requests, and also it will help attract more customers. Want to stay in budget, so Dream Bikes is a nonprofit, so we've acquired some budget from our mechanical engineering department as well as Innovate Grant. Want to comply with regulations just in case if there's any building codes. We want to complete our documentation before we get out of here. And we need our client's approval of prototype selection as well as that final design to achieve customer satisfaction. Here are some of the assumptions we made. We assumed that our institution is going to provide some assistance for us, mainly in terms of the machine shop resources, some of the grants and mechanical engineering department funding. From our we assume that we're going to be able to see Dr. Armstrong every week. And from our team, everybody's healthy, everybody's here every week. And lastly, we want to make sure we have our client support, which means one, if by the time we need bikes from our clients, they're able to deliver some of the bike parts to us so we can reinforce our structure or build it into parts that we need. And also at the end, when we deliver the solution, we needed a clear working area so we can assemble the solution. Here are some of the constraints we identified concerning budget, deadlines, resource limitation, product quality, safety, logistics, and risk. So for target audience, we have primary, which is our clients, staff of Dream Bikes. Secondary is the local community of Milwaukee, so the potential clients that will walk in and browse the bicycles. And the tertiary audience is our institution, Milwaukee School of Engineering. Here are some of the stakeholders. Represented by Dr. Armstrong is our institution, which is the project facilitator. Us students is the project team making the product. And Mr. Manzanet is the store manager for Dream Bikes Milwaukee, who's our client. Here's our project roadmap. We first started figuring out the scope and estimating the budget at the same time in early August. We moved on to design concept in October and went through 2 main stages. So we were narrowing down our designs into 8 final designs, went through a decision matrix analysis. Then we narrowed it down to 4 designs, which we'll deliver to our clients for them to select, and we'll build the product of our client's choice. Final report was just submitted on Monday, and we're currently stepping into the modeling phase. And there's a clock here because winter break.
To start talking about our design, our design phases, we have to start with some guiding principles that we had. The main one, like I've said before, was sustainability. Because Dream Bikes takes donated bikes and refurbishes them, we wanted to add it to our solution to, one, reduce the material usage so that we can show, sustainability and greener engineering is more possible, while also saving on costs a little bit, because rather than taking like machined and engineered materials, we're taking these bikes and just being able to put it in there. Next 2 pillars, not far apart, is accessibility and aesthetics. We wanted to make a solution that was easy to load and unload bikes so that customers and employees can easily interact with the bike rack so that sale can go faster, plus it limits injury. With this, we also want to accommodate various kinds of bikes because there's not one fit all bike. There's trek, mountain, so on and so forth. So each of them have their own challenges on holding or being able to store. So we wanted to have the accessibility of different bikes. And then lastly, we want it to look nice. If it looks nice, more people are going to see it from the outside or stay in and be intrigued to look at it. While also we want to increase the visibility of these bikes because, hey, you get to see the bike that you possibly are buying. Then our first phase was we employed value engineering. With this, we brainstormed and wrote down the functions of an ideal bike rack or a bike solution that we wanted. And what we did is we put them in a simple verb and a quantifying noun, and then rank them with the functions of primary, secondary, and tertiary. With this, it helped us conceptualize what we wanted in our preliminary and final designs and what functions we wanted them to have. To better put this into perspective, we placed it into a fast diagram. And with this, it's a fantastic way to understand how each function flows into each other. How it can be read is from left to right is how. So an example, sell bikes. How do we do that? By holding bikes. How do we do that? By increasing stability of bikes, so on and so forth. And to read it from right to left is why. Increase the stability of bikes. Why? So we can hold bikes. Why? So we can sell bikes. Now, then, what we did is we made a bunch of preliminary designs, took them, boiled them down to a final 8, and then ranked them based off this criteria. The 5 zone is similar to our guiding principles, safety, ergonomics, and aesthetics, so that it's safe, easy for a human to use, and also looks nice. The 4 category was resources needed, mostly with MSOE and Dream Bikes provided to us, finding bikes in visibility and capacity. The 3 zone was the ability to incorporate recycled bikes and the cost. And the cost was within the budget that we have won from the mechanical engineering department and the in-event grant. The 2 categories are very in tandem with each other. Time to make and ease of assembly are very close, because if it's easy to assemble, it will be easy to make. And if it's as simple as it is, it'll be easy to maintenance. And then ease of transport is the 1, because you got to move it once. Now I'm going to go through each of the designs and just quickly go through them. So it was T-post, sign, tree, bike cleaner, paint roller, tensegrity, Lifty Boy 2, and half pirate ship. All of these designs were taken. We took the crucial aspects of each of them and boiled them down into the final 4 designs that we went with.
The first design that we decided to investigate was this carousel design. Its main advantage is that it combines aspects from many different designs that we had thought of. As you can see, the arms will raise and lower, which is reminiscent of the Lifty Boy 2 design. A cable will be connected to the ends of these arms here and connected up to these pulleys, where an employee can pull on the end of the rope that's hanging from the other end of the pulley and lift the arms up, which will then be locked in place with some sort of locking mechanism that we haven't investigated yet. It also has a carousel aspect of it. If you just push on one of the arms, the whole thing will spin. This carousel design is what our client originally came to us with in his project proposal. He wanted a design that was reminiscent of a carousel, so this includes that aspect. Its main disadvantage is that it only holds 10 bikes without interference. It was designed to hold 12 bikes, but as you can see here, the innermost bikes will interfere with each other, so 2 of them will have to be taken off too, making it only fit 10, which is a lot less than the client had hoped for. Currently, they are just putting bicycles on their floor and they can hold 20 bikes doing that. So this will be a big downgrade in the amount of bikes that they are able to hold. We started our analysis by creating free body diagrams of the arm in both the horizontal and a 45-degree position, as these will be the resting places. The reaction forces of both the cable and the post were analyzed and summarized in these tables down here. And then the 2 critical locations that we decided to investigate further were the arm and the central post. The arm was decided to be analyzed as it will be made out of wood, and if it fails, it will be a relatively catastrophic failure. So we just wanted to make sure that it would be able to hold the weight of the bikes. So we modeled that in ANSYS and applied the loads of the bike, as well as the weight of the arm itself. And then we also analyzed the central post, as we were afraid of bending if it were unevenly loaded. We also modeled this in ANSYS and applied 2 reaction forces perpendicular to each other, which would be the reaction forces found in the previous step from the cables. They were applied perpendicularly to each other, as this replicates two arms that were fully loaded, and as if the other two arms were not loaded. This would be the worst case scenario loading condition. Both were found to have factors of safety of 7 and 20, which is very good factors of safety and not at risk of yielding.
Thank you. The next two designs we're going to take a look at both utilize the same mechanism called the bike lever. On the left, we have a linear design, which holds about 32 bikes. And on the right, a circular design holds about 24 bikes. Should the client want, the circular design could rotate. So the bike lever mechanism is shown in the bottom left. All that's needed is the bike is pushed along the floor. The lever will pivot to a stable vertical resting position, and the bike is held there. This has the advantage of being very ergonomic. This will allow both employees and customers to use this to load and unload bikes. The disadvantage, because it is a rotating mechanism, oil will need to be routinely applied to the base of the lever to keep it operational. On the right, we have a possible design of the lever that utilizes a minimum of bike frames from 4 bikes. So FEA analysis was performed on the lever itself, but due to high factors of safety against yield and buckling, it was deemed not likely to fail and therefore not a critical component. However, high moment reactions were found at the base of the lever. These will be investigated in the next semester, and the hinge that is at that location, which is a main point of concern, will be designed to resist those reaction moments and reaction forces. Those moments and forces were verified using the equations on screen and a quasi-static analysis. And some of those hand calculations are shown on these 2 slides. Feel free to look through them in the handout or ask at the end.
Thank you, Kelly. The fourth and final design is this large hex tensegrity model. You may have noticed in our final 8, we had a tensegrity model that was initially proposed by Letian over here, and we thought it was really cool. So we decided to stick with it and try to incorporate it into a final design. You can see here on the left is a unloaded model, and to the right is a fully loaded model. This tensegrity model has a capacity of roughly 42 bikes, which is significantly more than what he has on the floor right now at Dream Bikes. But it also does have a very large footprint of roughly 16 feet by 14 feet, which takes up nearly all the space that we were allocated at Dream Bikes. Please also take note of these staggered hooks right here. These are a novel design. Basically, we're going to try and hold the bikes by their handlebars, which is different than a lot of large big box stores like REI, which hold bikes by the wheels. The client has indicated that he doesn't want the wheels to be held because it leads to warpage of the tires over time. So we're doing that here. Additionally, these hooks are a possible design, but depending on material availability at Dream Bikes, we are planning to make these hooks out of recycled bike parts, bike frames to hold the bikes up. So some reasonable questions are, what is tensegrity anyway? If you're uninitiated or haven't just seen a cool YouTube video of tensegrity, basically, it's just a clever mechanical design that uses alternating tension columns that you can see here, or better up here picture, and stability columns or cables. All these cables are in tension, but most of the weight is being held by this cable right here. Cables, rope, chain, they're very strong in tension, but they have no compression strength, basically whatsoever. So this design takes advantage of that, and it kind of gives this illusion of a floating top structure. So some advantages of this design are its high potential capacity of 42 bikes, which is more than any other proposed design that we have. And it also has this, as discussed, kind of inherent cool factor for any customer coming in. They might see the structure and be like, how are these bikes being held up? You know, basically we want an attention grabbing piece to deliver to Dream Bikes. That is one of the deliverables that we're trying to give them. Disadvantages of this design are it's very large footprint. It's way bigger than all the other ones. And obviously, as designed, it has a unusable space of the inside of this hexagon of roughly 150 square feet. So a possibility that we've discussed at length is just leaving one side open to open up the floor space for additional storage for bicycles or wheels or spokes. But that'll be discussed with the client in January. These are just some basic hand calculations just to see the feasibility of this structure itself. This is just a calculations to see how much tension is going to be on these cables in the tension columns. And that's roughly a little bit overestimated at 500 pounds per tension cable. And also the most critical part of this structure is the tension column, these little L brackets you see here. After applying that 500-pound tension force at the end of that short arm, is that short arm going to bend? Is it going to break? That's what we're most interested in because the integrity of the structure is based on that, mostly based on that alone. It resulted in a very low bending force on the short arm. So we decided to go with this design and this material of the 2-inch square pipe. We took that and we plugged in an FEA. And you can see the results here. There's going to be a through hole right up here on our short arm, and also obviously stress concentration from the weld right here. So we want to investigate that in FEA. Is this a concern? Will this thing yield when it's under the full weight? As you can see here, we did a Von Mises stress analysis just to get the equivalent stress on the short arm, and it resulted in a maximum stress at the weld of only 11.3 TSI, which is well below the yield strength of 836 steel, which is what we plan to use. And also only have a max deformation of 0.18 inches, which is 3/16 of an inch, which is not inherently dangerous in itself. This also has a high factor of safety of 3.2. I will also note that we just investigated the 4x4 framing, and I applied all these remote forces here just to check for twist or warping in the 4x4 structure itself. There was essentially no deformation as expected, but it was worth investigating anyway. And just, we want to present this to the client, just to let him know that this is safe for, if they choose this design, is this safe for your customers? And we can confidently say yes. So in this presentation, from the analysis that we have done this semester, we have overall concluded that all the designs that we've proposed for the final 4 are obtainable to construct with the resources allocated to us by MSOE and Dream Bikes. It also is, all critical points are in a very safe factor of safety, and also is within the budget that we have right now from the 2 grants we have won.
So this project is unique in that the final design will be in the store of Dream Bikes and will be interfaced by customers. Therefore, we have the 4 designs you saw versus a final design that other teams might have presented. The plan is next semester at the very beginning, we're going to meet with the client to get his opinion on what he thinks the final design should be based on aesthetics and what exactly he's looking for. Once we have that opinion and that decision made, we can create a final prototype to be used to further confirm the FEA models, as well as to iterate on towards a final design. That final design will be built and delivered to the Dream Bike store.
Thank you all in person and online for listening to our presentation. You can see in the appendix, there is the hand calculations for the carousel, the bill of materials for each of the 4 designs, and the final 8 decision matrix, and also the FEA of the bike lever. Thank you very much again, and any questions?
So at this time, we're going to do questions first from the panel, and then if there's any time remaining, we can take some from the audience. So I'm going to go ahead and start the questions. First thing I wanted to compliment on the organization of your project development. So well-structured, well-defined, you could clearly see evidence of where everything was coming from in your process. So that was awesome. Getting into your tensegrity design, is there a reason that it has to have 90-degree corners for that that main structure that supports the cable? Or could you bend those so they're kind of like, I don't want to say all the way into a J turn, but bend at 90 degrees? Is there a way that you can do that based on the type of tubing that you're planning to use? Might be something to explore in that process. The other thing is as you get into that corner, really optimizing how you decide to put that weld in the corner, whether it's going to be a 45 miter, whether it's going to be a flush mount 90 on the side or on the vertical one. So depending upon where you want to see that stress play through that weld joint, and weld joint itself is stronger than the material right next to it, but there's that transition between the material that has the as worked properties when they drew the tube itself, as compared to what happens when you hit it and you put those stresses. So if you're planning on doing this on your own, make sure you understand how to remove all the internal stresses after that kind of weld takes place. If this thing really is going to have only 3 points that are supporting all the weight of that structure. The other question or concern I would have would be really defining that you've got the stability working, because the employees are going to have to be pushing and pulling as they're working bikes off of those hooks. And you'd like the structure to stay in one place while they're trying to do that, not have it shimmy back and forth, rotating or kind of push away from them and stuff. So think about how you might come up with some experiments that you could do to demonstrate that stability, whether they be physical, actual like model experiments, or whether they happen in a motion model, or even SolidWorks Motion, you might be able to get there. So those are the quick comments I had. And then one real question in your problem, it looks like you're looking at just one rack in the showroom, or are you looking at multiple placements in the showroom?
So I think Leitian, would you like to answer that?
Yeah, so what was there, sorry, Dr. Farrell, was there any question that you would like me to answer with regard to the tensegrity first?
No, so you did a great job defining what you were doing with the tensegrity design.
Yeah.
I just wanted to give you those extra inputs as you're finalizing, if that's the path that you're finalizing along, that you pay attention to those details, so that you've got what you want.
Yeah, thank you. So with regard to the discussion on like how many discrete, I think, modulation we're going to have within the space, initially we had, in the very early beginning, we discussed what if we just make repeatable parts and just arrange them in the space. But looking at the grants that we got, we figured that we had enough budget to build one larger structure. And also we had in the middle of our review of our very first 16 designs to begin with, our advisor, Dr. Armstrong, was a little bit concerned about how visible the bikes actually are. If we're building modular designs that have smaller footprints, that also puts a limitation on how high we can build the thing. And our client's floor space has how many feet of clearance height-wise?
About 12 feet of clearance to the ceiling.
Yeah, so if we're building smaller parts, we cannot stack higher. And that's why we went on to say, why don't we just make something that takes up the just majority of the space, and if our client wants something else, we can put it in storage.
And to hop on that a little bit, you talking about the general space, what was allocated to us was related to their whole space. They have in the middle of the showroom, they have about 2 columns, and in between those 2 columns is where we were allotted that space. I believe it was about 243.
It's about 240 feet wide by about 130 in depth.
About inches.
Yeah,
So it's in
yeah.
inches. So that was our footprint, was this area between the 2 pillars.
Okay, let's see, Dr. Armstrong, do you have any questions that you want to share with the team?
Okay, I'll catch up with them on our next meeting if there's any
Sounds
other
good.
questions in the room there.
So I'm going to open up to the floor. Are there any questions or comments that people would like to deliver? So let's.
I have a question. For the tensegrity design, I was wondering if you had done any analysis or FEA on the anchors you would use for the cables that are interfaced with the steel piping.
As far as FEA, no, that's just kind of going off of the specifications on rigging that I've done in the past, just using eye bolts, and just kind of analyzing that and what's the maximum force that's going to be placed on the eye bolt and the wood that's attached to. It should be nowhere near yielding on the eye bolts or the cables. We chose specifically a 3/8 inch cable, which has a tensile strength of roughly 15,000 psi, and that's far more. Or the yield strength for that is way too high for bikes and the way the structure itself.
So I'm going to add a quick comment in there. For attaching cables to rigid ends for a structure like this, you may want to go over and consult with the civil engineering group, because they actually, in their steel design, they look at cables interacting with rigid frame structures and how those ends have to be attached to meet code. Now, that's for a building structure,
Yes.
but it would give you insights to what's going on in your frame. And there was one more quick question, hopefully.
So, I was curious, have you guys done any analysis on the tensegrity design? If they have to pull bikes off of opposite sides due to stability? Or if they have to and like you said earlier, you're worried about the internal space, right? And removing half of the rack would move your weight disposition over, correct?
Yeah.
So that would also, you'd also have to think about that for stability. I'm just giving you guys some things I just thought of immediately, but I thought it was just curious. Yeah, I think I can take that one to start at least. The plan was to remove just one face of it, so we would still have the 6 points of contact, as well as to answer the question about if it's like unevenly loaded. I think Joe can answer that best.
Yeah, so assuming this design is chosen by Mr. Manzanet, we have been working with Dr. Rizza and other people familiar with ANSYS Mechanical to do kind of some simulations, just to see what would happen to the structure, because we can kind of model that better. It could be that maybe we get rid of the stability columns and we just use more tension columns, or we can see what we need to do to increase the rigidity of the structure, whether that's a higher tension in the stability cables to hold it more straight up and down. The weight of the bikes themselves is very minimal, based on the capacity of this. It's made of 4x4 posts, and the bikes aren't that heavy. Yes, but we'll see. We're going to do an analysis if this design is chosen.
Yes, and add just one last sort of thing to that is, excuse me, when the cables are tensioned to the specifications to hold everything up, it will not, the shift will be very minimal, and therefore will the minor shifts will correct itself in the cables. So major tipping will not happen. We did consider that and looked a tiny bit into it, but we'll be doing further analysis of that next semester.
In all your designs, did you account for like the largest bike size that you could have? Or
Yes.
did you,
Yes.
because if you have wider wheels, is that gonna be able to also fit there?
Yes, for every design, we assumed from what we have gained from either Dream Bikes providing to us or from just online sources, we assumed the widest handle, heaviest bike, and we assumed just most of like the extreme cases, and all of them do succeed and can accommodate for all of those, designs.
And just for reference, if you put a bike in its own space, it's about 2 feet wide. Like you need a 2 feet width to put the handle in. But if you put it in the staggered, it's about 32 inches for two. So we also have discussions about the packing regime. How do you put the pedals in there? How do we can we get one bike out between two, and how the corners work? So all that kind of stuff were considered, and that's why some of the numbers I personally believe are lower estimates on capacity. So yeah.
Also, correct me if I'm wrong, but I heard at the beginning of your presentation that you were trying to reuse parts of all bikes to build.
Yes,
How is that implemented into this structure?
the tensegrity.
Yeah.
For the tensegrity, it would be the hooks, because those themselves can just be made out of bike frames, or what we have thought is the fork of a bike. When you're thinking about a bike, the thing that holds the actual wheel that has a spoke through it, it kind of just looks like a two-pronged fork. What we thought about is taking that design and bending, and also this is just general ideas. So we thought about just bending those and then reusing them for these hooks, or in general, taking just other thicker parts of the bike, like the bike frame, and just machining them to be able to hold.
Yeah. So yeah. Oh, sorry.
So we really have
yes,
to
sorry.
wrap up the session. We've gone over time. And so I'm gonna go ahead and close this off. I want to thank both teams. You did a great job. And here at online, I'll be getting you, I'll scan and get you this form. If you'd like to take a look at the notes that I wrote down on it, I will send that to you. Otherwise, take care.
Thank you. Thank you for chairing the session, Dr. Farrell.
You are